I hope you are doing well. I came with another video to introduce mean norm method, a method for frequency estimation of complex sinusoidals in white noise. Previously in this channel, I presented two methods, music method and spirit method. And now I'm gonna talk about mean norm method. All of these methods are based on subspace. We call them subspace method. In the context of array processing and sinusoidal frequency estimation, the structure of correlation matrix of our array or our receive signal is as A, P, A Hermitian plus sigma 2 I M. R is M by M matrix and A is an M by N matrix that is a van der Waals matrix, and the structure of A is A omega 1, A omega 2, A omega n. Omega 1 and until omega n are our frequencies that we are gonna estimate them based on this method, using these methods. The structure of A omega is 1 e minus j omega e minus j 2 omega until e minus j m minus 1 omega. We are trying to estimate R based on data samples or in array processing based on snapshots we received, and then we try to use these algorithms which are based on the correlation matrix. The first thing that we do in subspace methods, we do eigenanalysis of correlation matrix. I divide eigenvalues and eigenvectors of correlation matrix in two main spaces: noise subspaces, which is based on matrix G, which is M by M minus N matrix. It's based on eigenvectors corresponding to M minus N lowest or smallest eigenvalues of R. M minus N smallest eigenvalues. And signal subspace is based on based on S matrix, which is an M by N matrix. This matrix is also the form of this matrix is based on the eigenvectors of R, but this time eigenvectors corresponding to n largest eigenvalues of correlation matrix. N is the number of sources or number of frequencies that we assume it is noun. Previously in this channel, I discussed about the music algorithm. Music algorithm is based on noise subspace. Spirit algorithm is based on signal subspace. Now I'm gonna introduce another method that is also based on noise subspace. Similar to music algorithm, min norm method is also based on the noise subspace. Unlike the music, minimum norm only uses one vector in range space of G. But music uses m minus n vectors. Uses all vectors in G. But in min norm method, we use one vector. That is why we want to introduce min norm method. The computational complexity is lower than music algorithm because here we only use one vector. It is also reported based on simulation the false peaks in pseudo-spectrum of min norm is lower than music. These advantages motivate us to introduce one min norm method. Before I dive into the mathematics of min norm method, I just want to introduce the pseudo-spectrum for min norm method. Min norm method uses one vector in range space of G. The form of this vector is 1 and G belongs to range space of G. This vector has minimum norm among all vectors like this in range space G. The main property of this vector that we have to select for minimum norm, it is its minimum norm property. Then I can form pseudo-spectrum P omega or S omega is 1 over A Hermitian omega 1 G power of 2. This is the pseudo-spectrum of min norm method. And the locations of frequencies are actually n highest peaks in this pseudo-spectrum. And we can easily, similar to music algorithm, by finding the n peaks of this spectrum, the locations are estimate of our frequencies. And G is equal to G bar beta norm beta power of 2. What is G bar and beta? If I partition G like beta Hermitian and G bar, this is the first row of G, and other rows actually G was a matrix M by M minus 1, so other M minus 1 rows of G, we call it G bar. Let me repeat this. Beta Hermitian is the first row of G, and G bar is the other m-1 rows of matrix G. I form this vector beta and this matrix G based on their noise eigenvectors G. And then by using this formula, I can find G, and finally by substituting G in this formula, I can form pseudo-spectrum. We call this mean norm. But I have to continue and discuss in details how I can find G in G. We know the vectors in S and G are orthogonal. I can use this property. Our vector 1 and G belongs to range space G. And I partition S alpha Hermitian S bar. This is the first row of S, and this is other m-1 rows S bar. It means S bar is an m-1 by n matrix, and alpha is n by 1 vector. Based on the orthogonality, S Hermitian 1 and G equals to 0. That means alpha S bar Hermitian 1 G equals to 0. This gives me an equation: alpha plus S bar Hermitian G equals to 0. S bar Hermitian G equals to minus alpha. This is a linear equation that should be solved. This is an underdetermined equation. I can find the solution for this based on least squares. This solution has this feature that G has a minimum norm. I mean, the solution that I give for this problem has the property of minimum norm solution. So least squares give me this solution: G equals to minus S bar Hermitian S bar inverse alpha. Least squares minimum norm solution. Okay, let's continue and try to find the final equation for G. We have S bar Hermitian S bar plus alpha Hermitian equals to I. Where this formula comes from? We have S Hermitian S equals to I, because the vectors, the eigenvectors in S are orthonormal. So S bar Hermitian S bar equals to I minus alpha Hermitian. If I multiply the right side of this equation with alpha, I can obtain S bar Hermitian S bar alpha equals to alpha minus alpha norm alpha power of 2. And if we multiply both sides by S Hermitian S bar inverse, I can get S bar Hermitian S bar inverse alpha equals to alpha over 1 minus norm alpha equals to 2. Actually, norm alpha power of 2 must not be 1. If we look at this formula, this is actually rank 1 matrix, and the eigenvalues for this matrix is norm alpha power of 2, and the eigenvalues for I is 1. So one of eigenvalues of S bar Hermitian S bar is 1 minus norm alpha power of 2, which must not be 0, because if this is 0, then the inverse of S bar Hermitian S bar doesn't exist. So S bar Hermitian S bar inverse exists if 1 minus norm alpha power of 2 must not be actually 0. And we can see here in this. So in previous formula, I can replace S bar Hermitian S bar inverse alpha with alpha over 1 minus norm alpha power of 2, and I will find this formula minus S bar alpha 1 minus norm alpha power of 2. This is one formula for G, but that is not the final formula that I introduced in the first slide. Let's continue to find the final formula for G. For finding the final formula, I'm gonna actually develop a formula based on the G. At the moment, I reach to a formula based on the S. I want to change it. I can use these features S Hermitian plus G Hermitian equals to identity matrix. Why? Because eigenvectors of R positive differential symmetric matrix are orthogonals, are orthonormals. So I can write them like this: S Hermitian plus G Hermitian equals to I, and I have S Hermitian equals to I minus G Hermitian. And using the partition that I have, if I replace S and G based on the partition form, I will get S Hermitian is norm alpha power of 2 S bar alpha Hermitian S bar alpha S bar Hermitian equals to 1 minus norm beta power of 2 minus G bar beta Hermitian minus G bar beta, and finally I minus G bar Hermitian. Now we can see norm alpha power of 2 equals to 1 minus norm beta equals 2. That means 1 minus norm alpha power of 2 equals to norm beta power of 2. And another equation, we have G bar beta equals to minus S bar alpha. Look at the formula that we obtained for G, and I can minus alpha, norm alpha power of 2 is norm beta equals power of 2, and S bar alpha minus S bar alpha equals to G bar beta. And finally I can write G based on G bar beta norm beta power of 2. This is the final formula for the vector G. We reached to the final of this video. I hope you like it. If you like it, and if you want to see more videos regarding signal processing and array processing, please subscribe my channel. Thank you for watching this video.